Hi, I'm Ashutosh. In this video, I will be presenting the work that I did in collaboration with my colleague Dr. Ivan Rachkin and my mentors Dr. Bradley Schrammel and Professor David Carlin. Let's take a look at an example of a self-adaptive system, Netflix, which has to provide high availability and optimal performance despite changing environment, faults, and attacks. Netflix primarily cares for throughput because it is a proxy for the latency perceived by its users. Maintaining overall latency is critical for a good user experience. If the workload increases, the latency of response might also increase. In this situation, Netflix needs to quickly come up with a plan to reduce the latency. For example, the system can add a server, but adding a server would increase the operating cost for Netflix. Ideally, for emergencies such as high latency, Netflix would like to come up with a plan quickly that provides long-term utility by balancing different quality attributes such as keeping the latency of response time lower, using minimal resources to also keep the cost lower. Therefore, for systems such as Netflix, both timeliness and quality of planning is important. Unfortunately, it is difficult to decrease the planning time and increase the planning quality at the same time. These qualities are fundamentally conflicting in nature. Here is a system inspired by Netflix that I will use throughout the talk as an example to explain concepts. Also, this system is one of the systems used for evaluating the ideas proposed in this paper. In this cloud-based self-adaptive system, users send requests to the load balancer. The request arrival rate depends on users, therefore varies in an uncertain manner, leading to variance in the system's workload. On receiving the request, the load balancer assigns the request to different servers. As you can see, there are different types of servers that differ in their ability to serve requests per second and cost. Intuitively, the server with a higher capacity to serve requests per second has a higher cost of deployment. Suppose initially a server of type B is active. If the workload on the system increases beyond the capacity of the server, the system can add more servers, possibly of different types, to manage the workload. However, as more servers are added, the operating cost also increases. Here are the goals for the system. Maintain response time below a predefined threshold, say T, decrease operating cost by minimizing the resources to serve the clients, and increase revenue by serving clients' requests. Suppose the system runs for duration L. Here is the utility function that gives us aggregate utility obtained over duration L. You don't have to go through the details of this function. Just pay attention to how different goals are captured by this multidimensional utility function. Such a utility function captures both the quality and the timeliness of planning. The function captures quality since it has various adaptation goals as constituents. Timeliness is captured by this function since there is a penalty for high response time and therefore the system needs to react quickly to lower the penalty. However, as I mentioned earlier, it is difficult to decrease planning time and increase planning quality at the same time. To find a balance between timeliness and quality of planning, in our previous work, we proposed the idea of hybrid planning. The idea of hybrid planning is about combining off-the-shelf reactive and deliberative planners to balance the timeliness and quality of planning. Throughout this talk, I will be using the term planners and planning interchangeably. Both the terms represent a component that takes a planning problem as an input and returns a plan. Hybrid planning uses reactive planning to provide a quick but potentially a suboptimal plan, but uses deliberative planning to provide a plan that improves quality in the long run. To further explain hybrid planning with a simple example, suppose at time t, a system faces a planning problem. A planning problem, broadly speaking, captures the state of the system and the environment, state action transitions, and the desired state of the system. Suppose the system has a deliberative planner and a reactive planner. Deliberative planner provides high quality plan. Therefore, on observing the planning problem, the system invokes the deliberative planner at time t, which determines a quality plan at time t prime. This quality plan is then executed from t prime onwards. However, the system is just waiting for a deliberative plan to be ready between time t and t prime. And in case of an emergency, waiting might be a problem. Therefore, to provide a reasonable response, between time t and t prime, the system invokes reactive planning, which suppose provides plan in a negligible time. So this reactive plan is ready at time t. This reactive plan is then executed between time t and t prime, and the deliberative plan takes over the execution time t prime onwards. In our previous work, we showed that by combining reactive and deliberative planners, systems can achieve higher utility compared to using these planners in isolation. By now, the idea of hybrid planning might sound appealing to you, but there are two fundamental challenges to the implementation of hybrid planning. The first challenge is the planning selection problem, which is about choosing an appropriate planner from the set of planners used to instantiate hybrid planning. For example, while deliberative planning is in process, a blind application of suboptimal reactive planning could lead a system to a permanent failure state. Therefore, it's important to know if reactive planning should be applied or it's better to wait until a deliberative plan is ready. Solving this planning selection problem is the main focus of this paper. The second fundamental challenge is the planning coordination problem, which is about guaranteeing a seamless transition from a reactive plan to a deliberative plan. Guaranteeing this seamless transition can be non-trivial, particularly under uncertainty. Our solution to this problem is discussed in one of our previous work. For this talk, we will assume that the transition between a reactive plan and a deliberative plan is guaranteed. Our work has two key contributions. First, a learning-based solution to the planning selection problem. Second, guidelines to instantiate hybrid planning. These guidelines are based on the empirical analysis of the data obtained from the two case studies used to evaluate our solution to the planning selection problem. We expect these guidelines can inform designers who need to prioritize their investment of resources in planners instead of exploring many possible combinations to instantiate hybrid planning. Now I will discuss our approach to address the planning selection problem. Suppose hybrid planning is instantiated using a deliberative planner and a set of reactive planners. We assume that deliberative plan provides higher or at least equal expected utility compared to the reactive plan determined by any of the reactive planners in the set. Therefore, when a deliberative plan is ready, it by default takes over the execution from a reactive plan. Given this assumption, here is the definition of the planning selection problem. Given a planning problem and a set of reactive planners, choose the planner that will provide the highest utility when used in combination with the deliberative planner. One approach to solving the planning selection problem is the condition-based hybrid planning. In this approach, at design time, system designers identify conditions to invoke reactive planning. Whenever such a predefined condition is satisfied, reactive planning corresponding to that condition is invoked. For example, in the context of the cloud-based system discussed earlier, system designers can decide at design time that whenever there is a response time constraint violation, invoke the reactive planner. If we look at the related work to solve the planning selection problem, when multiple planners are combined, they suggest different variations of the condition-based invocation of reactive planners. Netflix also deployed the condition-based hybrid planning for its auto-scaling solution. The advantage of the condition-based hybrid planning is that it is easy to apply when determining conditions at design time. To invoke reactive planning is straightforward. However, there are also certain disadvantages of the condition-based hybrid planning. First, it requires domain expertise to identify the conditions that should trigger reactive planning. Second, it relies on error-prone humans to identify the right and comprehensive conditions. Third, it hinders reuse of hybrid planning since such conditions do not transfer to other systems or domains. To overcome these drawbacks, in this paper we propose a learning-based approach to solve the planning selection problem. So how does the learning-based approach works? It is a supervised learning approach that has two phases, the offline or the training phase and the online or the deployment phase. In the offline phase, we have a set of labeled planning problems for training. The label of a planning problem indicates which reactive planner, when used in combination with the deliberative planner, is likely to provide the highest utility compared to other reactive planners from the set. We used features to represent the problems. The paper discusses our feature extraction approach in detail. Then, using a machine learning algorithm, we build a classifier that takes a planning problem features as an input and outputs the reactive planner to be used for that problem. Essentially, this classifier solves the planning selection problem. This classifier is then deployed to be used during the online phase. In the online phase, when a system observes a planning problem, the same feature set is extracted for the problem and passed as an input to the classifier, which returns the label for the problem indicating the best reactive planner to be invoked for the problem. As you can see, the learning-based approach automatically learns the conditions to invoke reactive planners. However, the application of this supervised learning technique is not straightforward. To train a classifier, one needs a set of labeled training problems. Labeling a planning problem requires to estimate which reactive planner from the set, when used in combination with deliberative planning, is likely to provide the highest utility for the problem. To this end, for the planning problem, one needs to evaluate each reactive planner in combination with the deliberative planner. For a training planning problem, the evaluation of a reactive planner would look something like this. Suppose this is a state action transition representation of the planning problem with the initial state S. The deliberative planning time for this problem is Td. To evaluate the reactive planner, until time Td, we need to evaluate the performance of the reactive plan PR determined by this reactive planner. And after Td, the deliberative plan is evaluated. This evaluation will inform how the reactive planner will perform in combination with the deliberative planner. However, this evaluation is non-trivial, particularly in domains with uncertain dynamics, which is often the case in modern systems. In such domains, the environment evolution and the outcomes of a system's actions may change between attempts. So one would have to perform multiple trials of the same combination to determine the best average outcome. For example, in this figure, one needs to execute the combination of the reactive and deliberative plan multiple times unless all the execution paths are covered. To solve this problem, we propose using probabilistic model checking to estimate the performance of reactive planning and deliberative planning. Probabilistic model checking evaluates the combination over all possible execution paths in a planning problem with a single run of a model checker. More details can be found in the paper. As an input, a probabilistic model checker takes a planning problem, reactive and deliberative plans for that problem, and the deliberative planning time. The model checker outputs the expected utility of the combination of the reactive and deliberative plan. The expected utility is a real number indicating the performance of the combination. Here is the general algorithm for the labeling process. For each training problem, find the reactive plan determined by each reactive planner. Find the deliberative plan for that problem. Evaluate the combination of the reactive plans with the deliberative plan using probabilistic model checking, and pick the reactive planner with the maximum expected utility. Next, I will present the evaluation of the learning-based approach compared to the condition-based approach. But first, let's understand the experimental setup. To evaluate the learning-based approach, we use two realistic systems. First is the cloud-based self-adaptive system as discussed earlier in the talk. As the second system, we used a simulated team of unmanned aerial vehicles UAVs performing a reconnaissance mission in a hostile environment. The predefined route of the team is a straight line divided into equal segments of fixed length as shown in the figure, where segments are divided by vertical lines. Each segment can have threats and detection targets depending on how they are randomly placed in the route. The mission of the team is to detect the targets and avoid being shot down by the threats, which would lead to mission failure because no more targets can be detected further. The team has some adaptation actions such as increasing and decreasing altitude to maximize the number of targets detected, taking into account that if the team is lost to a threat, the mission fails. If the team chooses to execute an action, then all of the team members execute the same action. The team has different sensors to detect targets and threats as it flies a route at a constant speed. Due to sensing errors, The sensor's reports may include false positives and false negatives. Therefore, there is uncertainty in the detection of threats and targets. For hybrid planning in both the systems, we instantiate deliberative planning with MTP planning, which takes uncertainty into account, therefore likely to find quality plans. The set of reactive planners for both the systems has a special element R-wait that for any planning problem always suggests to wait until our deliberative plan is ready. R-wait is added to the set to ensure that hybrid planning does not underperform when deliberative planning is used alone. When using hybrid planning, in cases when none of the other reactive planners provide a better plan than just waiting for the deliberative plan to be ready, R-wait can be selected. As supported by our evaluation results, in certain situations it is prudent to just wait. In addition to R-wait, the other reactive planner for the cloud-based system is deterministic planner, which ignores uncertainty. For the UAV team, besides R-wait, the second reactive planner is MDP planning, but with a shorter horizon compared to the deliberative MDP planning. In addition, this short horizon MDP planning uses only a subset of actions compared to deliberative MDP planning. This shorter horizon combined with the subset of actions leads to a smaller state space compared to deliberative MDP planning, and therefore reactive planning time is negligible compared to deliberative planning. Going forward in the talk, I will use the term non-wait reactive planners to refer to deterministic reactive planner for the cloud-based system and short horizon MDP planner for the UAV team. To generate training problems for the cloud-based system, we used FIFA World Cup traces as a representation of a realistic workload. In total, 1651 problems were generated for training. On labeling the planning problems using probabilistic model checking, 111 problems were labeled as R-wait, meaning for these problems, waiting was the better option compared to using deterministic planning. For 253 problems, deterministic planning was found to be better than waiting, and the remaining problems were labeled as use either, meaning both the wait planner and the deterministic planner provided equal performance. Keep this use either label in mind, as I will refer it again in the next slide. For the UAV team, we used 630 different missions to generate planning problems, which were labeled in the same three categories as the cloud-based system. For evaluation, in the hybrid planning mode, we have two broad categories, the condition-based and the learning-based hybrid planning. In the condition-based hybrid planning, for the cloud-based system, deterministic planning is used when response time goes above the threshold. For the UAV team, the short horizon MDP planning is used when the UAVs are in the range of threats on the ground. Learning-based hybrid planning has two modes. If the classifier labels a planning problem as use either, then which of the reactive planners should be used, wait or non-wait? To resolve this ambiguity, we introduced two modes. The first is learning-based reactive mode or LBR. In this mode, whenever a planning problem is labeled as use either, we use non-wait reactive planner. The second is learning-based wait mode or LBW. In this mode, whenever a planning problem is labeled as use either, we use wait planner. Now I will present the evaluation results to compare the learning-based approach to the condition-based approach. For the evaluation, we compared the performance of the two approaches in terms of the utility accrued for different workload traces and UAV missions. In addition, I will present some of the key guidelines to instantiate hybrid planning. In this bar chart, we compare in how many traces and missions one planning mode provided higher or equal utility compared to other planning modes. Let's focus on these four bars that compare the performance of the learning-based and the condition-based hybrid planning for the two systems. The bar in the top right corner compares the learning-based reactive mode or LBR with the condition-based approach for the cloud-based system. We see that for most of the traces, LBR mode either provided higher or at least equal utility compared to the condition-based approach. The outperformance of the learning-based approach is even more significant for the UAV team, where out of 70 test missions, the condition-based approach could not provide higher utility even in a single mission. The paper also discusses that this data showing the outperformance of the learning-based approach is statistically significant. Similarly, on looking at the left 6 bars, we see that both the hybrid planning modes, the condition-based and the learning-based, outperformed compared to hybrid planning constituent planners when used alone. This indicates that hybrid planning was able to better balance quality and timeliness of planning compared to its constituent planners. The bar chart in the previous slide compares the relative performance of the planning modes for each trace and mission. In this box chart, we compare absolute utilities accrued by different planning modes. Let me explain this box chart with the leftmost purple box on the top, which is for the cloud-based system. Recall, in the reactive mode for the cloud-based system, we use deterministic planning only. So the system just relies on deterministic planning mode for adaptation in the reactive mode. Here is how this box is constructed. Suppose for a workload trace, the condition-based approach gives utility U1 and using only deterministic planning gives utility U2. The difference between the utilities will be U1 minus U2. We calculate this difference for all the 87 test traces. Then using these 87 utility differences, we plot this box. The top and the bottom whiskers of the box represent the maximum and minimum difference. If you notice, the length of the top whisker is longer than the bottom whisker, indicating the maximum utility gain for the condition-based approach was higher compared to the reactive only mode. The horizontal top and bottom edges of the box represent 75th and 25th percentile respectively. The bottom edge for the box is at 0, implies for 75% traces, the difference between the condition-based approach and the reactive only mode is 0 or above. Therefore, for these 75% traces, the condition-based approach provided higher utility compared to reactive only planning mode. The horizontal line inside the box represents the median value of differences, which is also above 0. On similar lines, if we look at the two rightmost boxes for both the systems, we can conclude that the learning-based approach outperformed the condition-based approach, and by looking at the leftmost 6 boxes for the two systems, we can conclude that hybrid planning modes, the condition-based and the learning-based, outperformed its constituent planners when used alone. More analysis of this box chart can be found in the paper. Coming to the guidelines to instantiate hybrid planning based on the data obtained from the two case studies, here are the top findings. The first finding is that having an effective deliberative planning is the foundation for hybrid planning. On conducting chi-square test, we found that if deliberative only planning mode provides higher utility than reactive only planning mode, then hybrid planning is likely to outperform its constituent planners. We also found a strong to median Pearson correlation between the performance of hybrid planning and the performance of deliberative planning. Now, to choose between the learning-based and the condition-based approach, pick learning-based hybrid planning when identifying the predefined condition is not straightforward and adequate training data is available. The paper presents some more guidelines and discusses how these guidelines are derived from the empirical analysis of the data. Here is the summary of the findings. Hybrid planning can better balance timeliness and quality of planning than its constituent planners, but for that we need effective deliberative planning. The second finding is the learning-based approach outperforms the condition-based approach, but for that we need an accurate classification which depends on adequate training planning problems. Here is the summary of the talk. First, I talked about the timeliness quality trade-off for planning and discussed hybrid planning as a potential solution to handle this trade-off. Then I talked about the two key challenges to implement hybrid planning. In particular, I discussed the planning selection problem and proposed the learning-based solution that uses probabilistic model checking to label the training problems. This learning-based approach overcomes the drawback of the condition-based approach, which requires domain expertise and hinders the reuse of hybrid planning. Finally, I presented the evaluation results of the learning-based approach. This evaluation was done using two realistic self-adaptive systems. The evaluation showed that the learning-based approach outperformed the condition-based approach. Thank you.